imagine we're traveling toward a black hole. I've chosen to travel toward this black hole here, which is Sagittarius A star, because we have a picture of it. This is a picture that was on all the front pages of the newspapers a few years ago. Plenty of black holes. There are millions of black holes, billions, in fact, of black holes. And I would say that this is that's a most surprising and most beautiful discovery of the last years, that the universe is actually filled with black holes. We didn't know that. When I was a student, nobody even imagined that. In fact, people didn't believe that black holes could actually exist in the sky. So I could have chosen a much closer black hole. There are much closer black holes to go to, but this one is big. Is big, and we have a picture. We have a picture because is big. It's far in the center of the galaxy, so it's a long way to go there. But I want to take you there, and I want to take you next to it, and then into it. So what we are going to see if we get close. This image was taken by radio telescopes. In fact, some of you may know that, by having a number of radio telescopes on Earth working together, all around the Earth, half a dozen or more telescopes working as a single radio telescope. So if we go there, if we are going there, we're going to see something like that, of course, without the need of a huge radio telescope, because we are going closer and closer and closer. But when we go closer, we see it better, and that's what we're going to see. That is exactly the same images as the previous one, except that this one, the one we actually have seen, is out of focus because it's so far that the radio telescope cannot focus better. If it was more on focus, or what we expect to see with a technique for getting images gets better, is this one. In fact, this image was computed, was what was expected. Was theoretically predicted before the observation. And this is why, when we saw this one, it was so spectacular that, this is clearly something like that out of focus. So why a circle? The reason is a circle. It's far from obvious. First of all, just to make it clear, it would be a circle from whatever direction you would look at it. So it's not really a circle. It's an optical effect due to the funny way light moves around the black hole. Light around the black hole bends, because that's what we know light does next to masses, and that's how Einstein's theory that predicts all that tell us how all this works, was first confirmed by measuring the bending of the light by the star. And it bends in such a way that a ray of light could actually bend so much to be on an orbit around the black hole, in any possible angle, whatever angle. So around the hole is actually smaller than the ring. The ring roughly, as order of magnitude, is 1.5 times, the radius of the ring is 1.5 times the radius of the black hole inside. So you imagine, black hole, imagine for a moment like a black sphere, and around there is actually a sort of sphere of light, which is all the light that come from all over that start making some rotation around. So if you have, around this thing, there's a lot of matter, attracted by black holes, spiraling, doing funny things, and becoming very hot just because there is friction, there is clashing against one another. And imagine you have some light coming from here, this is black hole. You get the light directly, but you also get the light that bends around the black hole, roughly at 1.5 radius, and then get to our eyes. And light from here, you get the direct one, and the one come here. So you get a little bit of light from all over, and a lot of light from tangentially to that sphere, wherever you are. So wherever you are, you see this ring, which is a sort of meridian or equator of this sphere, from which tangentially the light comes to you from wherever. So this is the optical effect. that we see when we go there. So we get closer and we start seeing more clear this beautiful ring. We also approach all this matter moving around, but let's imagine that our starship or whatever is sufficiently solid that we're not going to be disturbed by that, and we get closer. We get closer, and let's do it slowly. We have rockets we can hold. Okay, there's a pool of the black hole, but we can hover at a certain distance from it by keeping the rocket firing. So we're keeping height, and we can look down, and down there is a hole. And this is big. This one, say, the actual dark thing is the size of the orbit of the moon. It's a huge thing. Okay, it's big things. It's bigger than the sun. And we keep at a distance. We look down. We see mostly see black, and we see things falling. Now, more precisely, imagine we're in our starship, we open a window, the stone falls down, we see it goes down, and what do we see? We don't see the fall entering the black hole, right? We see the stone slowing down, and never getting to the bottom. Slower, okay? Not only that, the light that comes from the stone, there's light there because there's all this burning thing, so it's not dark. It becomes dimmer and dimmer and dimmer and more red. So like the wavelength that light gets to us is more and more long, which means the frequency, it's slower and slower. It's like not only the stone is slowing down, but even its atoms are vibrating more slowly. But if you throw a clock down, we would see the clock slow down, slow down, slower and slower, almost stopping at some point when it goes there. Now we are there, since it's slow. Now suppose we look back, we look up from Earth, from where we came. And imagine, for instance, that from Earth we're getting messages. Say every day we get a message from our friends home. How is it going? Is it beautiful there? Okay, once every day. Okay, we get a message once every day, but when we're a distance from the black hole, we start getting messages every 20 hours. Then we come down a little bit toward the black hole, and we get messages every few hours. And then we come closer, and we get messages every minute. And then we get closer again, and we get one message every second. But from Earth, it was sent once a day. So we see the future, okay? We come all closer and closer, we get all these messages, with messages from 100 years in the future, 1,000 years in the future. That's time dilation. That's exactly the same phenomenon that on Earth we can measure in a laboratory. When we take two clocks, we move one up, wait a bit, come down, and the clock up measure a little bit more time, the clock down measure a little bit less time. Okay? That's done in the laboratory, except that on Earth is just a teeny fraction difference, the fraction of fractions, a millisecond, that can be measured. Near a black hole, which is a huge mass, this is enormous. But time dilation doesn't mean, of course, we're in the rocket, hovering there. For us, everything is normal. Time goes normal. Clock beats normally, my heart beats normally. But what we see closer to a black hole, we see it slower. What we see far away, we see it faster. So let's decrease our rockets and start getting inside the black hole. In the textbook, all the textbook of physics today, it's written that if you enter a black hole, that's it. You can never come out forever. So do we still want to get down? I mean, if we're going to die, we're going to die. We're also going to die if we stay out, because we're going to die anyway. But we have less time to live if we go in. But so we're in. We're inside the black hole now, and we're in. And let's look around. Okay. First, nothing particular has happened, right? Crossing the horizon, going into the black hole is the same. We are the same as before. Our starship is the same as before. If we look back at the stars, they're still the stars, all sort of out of position because light goes funny turns. But the lights come in and we see the star. But something is different. When we're outside, sort of hovering around, there was a sphere around the black hole, another sphere, and everything was there static, okay? And in the center of this sphere, there was this black hole, big, but certain size. Now we're inside. Imagine we can look around and see what is the geometry there. What we see is still, there are spheres and spheres, but below us is not just the volume we would expect. It's an immensely big volume. So spheres and spheres and spheres and spheres and spheres, down, 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 very far. So a black hole, it's you know these fairy tales that, you know, the two brothers, the sister brother walk in the wood, and then there's this little hut. And there's a door, they go in, and inside is a huge, huge room, and another huge room, and then a garden, fountains, and so on. A black hole is something similar. It has a size outside, but inside there's much more volume of what we are taught at school. You know, if there's a sphere of this radius, what is the volume inside? You can compute it. Okay, I never believe what they tell you at school. It's not true. There's a sphere in which the volume is much more than what they tell you it's inside the sphere. Why? Because space is distorted. That's what general relativity describes. The distortion of space is enormous. Imagine that this is the sphere around the black hole, the actual black hole. We were here. Now we move inside, we're in. And inside is much more than you would expect if this was flat. Okay, it's longer. There's this long tube, enormously long. The more the black hole is old, the more the tube is long. Okay. If there's some person here in the public here, or watching through a camera, who knows general relativity very, very well, might ask what I'm talking about. I'm describing a black hole in a peculiar foliation, which is the one I think is best to understand what's inside of the black hole, which is the foliation that maximizes the volume and that covers the entire black hole. So the first surprise is that there is this pit, this well, very, very profound. But that's not the biggest surprise. The biggest surprise, what we see there, is that it's moving. While outside, nothing was happening. We could have been hovering there forever. Inside is changing. The geometry of space is changing. Space around us is changing. And two things are happening. One is that it's becoming longer and longer and longer and longer with time. So that's why a black hole, it's bigger. Because with time, this becomes longer and longer and longer. It keeps growing. We're not talking of kilometers. We're talking about millions of light years. There's a huge, immense space inside an old black hole. Sagittarius A star presumably is at least 10 billion years old. It's very old, so it's a total cosmological age. So it's this immense thing. But the other thing is that it's shrinking. It's becoming longer and shrinking. Now, the fantastic people here at the RA build this beautiful thing, which actually becomes longer. I didn't know how to make it to shrink at the same time. Maybe so next time I'll get it to shrink. So if we are here, we are getting the sphere around us closing up on us. Okay, at speed which is pretty worrying. I mean, we don't have much time. This is closing around us. So here is a picture of an idea of this inside the black hole. And by the way, at the end, in this picture, you see a little dark spot at the end. So down here, I said it's very long, but I didn't say it's infinite. It's not infinite, right? It's finite. And then very bottom here, if some of you think there's a singularity, forget about it. There's no singularity out here. What is here? Here is a star that initially collapsed to form the black hole. So if there is some matter that at some point, most black holes we see, probably not this one, Sagittarius A star, but most stellar black holes that we see, the smaller one, are big stars that when they burn all the hydrogen, they cool down because they stop burning, they don't have fuel anymore. By cooling down, the pressure of the heat that was sort of keeping the star open diminish. So the weight is very big. The weight is so strong that they crush everything, and no rock would resist that weight, and they crush, and form the hole.